Hello students, welcome to this session of video. In this video we are going to discuss some of the probability distribution, and they are also called as theoretical distribution. And as far as syllabus is concerned, we have four distributions, namely binomial distribution, Poisson distribution, exponential distribution, and normal distribution. These are the last four distributions are there. But as far as binomial distribution is concerned, in order to understand the concepts of binomial distribution, a small background is required, which is known as Bernoulli distribution. That's why here we have listed the distributions to be studied as five, namely one is called Bernoulli distribution, next one is binomial, next one is Poisson, next one is exponential, next one is normal distribution. Out of these five, the first three distributions are discrete distributions, whereas the last two distributions are continuous priority distributions. Now, how they are categorized? Why we have to call these as discrete distributions and why we have to call these as continuous distribution? That all depends on the variable, or we can say that the nature of the variable underlying in those distributions. In the first three cases, the variable underlying is discrete in nature. That's why these three are referred as discrete distributions or discrete priority distributions. Whereas in the last two cases, the variable under consideration is continuous. That's why the last two distributions, namely exponential and normal distributions, are called continuous probability distribution. And then this is the, as far as the things we have to learn under the title theoretical distribution or priority distribution. Now let us start with the first one, that is called as Bernoulli distribution. Now, in order to study this Bernoulli distribution, first of all, we have to familiar with some of the basic definitions associated with that Bernoulli distribution. And the first one of that one is called as Bernoulli experiment or Bernoulli trial. Bernoulli experiment means any experiment which results in only two outcomes, namely one is called success or is called as failure, or called as Bernoulli experiment. Means any experiment which has only two outcomes, namely success and failure, are referred as Bernoulli experiments. Generally, the success is denoted by the number 1 or the letter 1, and the failure is denoted by 0. These are the conventions. Success is referred as 1 and failure is referred as 0. We can quote many examples for this Bernoulli trial or Bernoulli experiment. First, let us consider one example of experiment of tossing of a coin. When we toss a fair coin or a normal coin, it results in only two outcomes. Either it results in success, that is head, or it results in tail, that is failure. In this case, head is referred as success and tail is referred as failure. Therefore, this experiment has only two outcomes. That's why it is a good example of Bernoulli experiment. Similarly, we can quote one more example, that experiment of hitting of a target. When any shooter aims at a target, what are the possibilities? One possibility is the shooter may hit the target. In that case, we call it as a success, or the shooter may miss the target. In that case, we say that it is a failure. Overall, this experiment also has two outcomes. One is the target might be hit or the target might be missed. Therefore, it is also an example of Bernoulli experiment. And most familiar one, that is a result of the exam. Whenever the results of the exams are announced, if you take the overall result, the student will be in one of the category. One, he may be in the pass category or he may be in the fail category. Therefore, we can say in this case also that the result of the exam is a good example of Bernoulli trial or Bernoulli experiment. And we may arise some questions. Sometimes the result might be withheld due to some technical reason. Okay, even though if the result is withheld and after sometimes when the result is announced, Again, the result of a student is in one of the category, either he will be in the pass category or he or she will be in the fail category. In that case also, it will be in one of the two outcomes. One is success, another one is failure. If the student passes, we treat it as success. If the student fails, we treat it as a failure. That's why again here also we find only two outcomes. That's why we can confirm the result of the exam is also a good example of Bernoulli experiment or Bernoulli trial. And the same thing we can define in one more variant. This is Bernoulli experiment you have defined, and a variable associated with the Bernoulli experiment is called as Bernoulli variable. And in the Bernoulli experiment, you have said that the experiment has only two outcomes. One is called success, another is called failure. Accordingly, the variable takes only two values, 1 when it is success and 0 when it is failure. And with certain probability, if we say that P is the probability of success and 1 minus P, that is a complement of success is failure, that is 1 minus P, we can set as. That's why we can define that the Bernoulli variable in this particular fashion, a random variable which takes only two values, namely 1 and 0. 1 refers success and 0 refers failure with respect to probability P and 1 minus P, where P represents the probability of success and probability of failure is the complement of this, that is 1 minus P of P, we can write it as. Again, once you look at the total, it results in 1. Therefore, any variable which takes only two values, namely 1 and 0, with respect to probability P and 1 minus P is called as Bernoulli variable, and its distribution is referred as Bernoulli distribution. And again, if you want to calculate the mean and variance of this, two things we require. One is expected value of x and expected value of x square. In order to get the expected value of x, we need the total of x into p of x. In order to get the expected value of x square, we need the total of x square into p of x. In order to get those, first let us calculate x into p of x and x square into p of x. First let us go for x into p of x. X values are here, p of x values are here. Once you take the product, 1 into p is p, 0 into 1 minus p is 0. And again the total of this is 1. And now we got x into p of x. Let us multiply that one by x in order to get x square into p of x. Therefore, that is 1 into p is again p, 0 into 0 is 0. Again, once you take the sum, its value seems to be p itself. Therefore, this is a table we have calculated. Based on this, first let us calculate expected value of x, that is mean. Mean is given by total, that is summation of x into p of x. And once you get the total of x into p of x, its value is going to be p. And let us go for expected value of x square, and it is given by summation of x square into p of x. Again, its value is going to be p once again. Therefore, variance is given by expected value of x square minus expected value of x whole square. And expected value of x, that is nothing but mean, it is p. Expected value of x square is p square. That is, if you take p common, that will be 1 minus p. Therefore, variance equals to p as it is, and this 1 minus p is denoted by one more new notation, that is q. In future, always that q represents 1 minus p. Therefore, variance is given by pq. Therefore, mean of the distribution is p, that is expected value of x, and variance of the distribution is pq. Now, the same thing here we have done in the tabular form. Is it possible to put the same thing in the functional form in order to call it as probability mass function? That's why we have to think in such a fashion that means you have to guess one function. In that function, whenever we take x equals to 0, it should result in p. And whenever we take x equal to 0, it should result in 1 minus p. Okay, you try that one in taking the rough, and I'll give the functional form of that. That is, we say that a discrete random variable which has the following probability mass function, that is a p of x equals to p raised to x into 1 minus p raised to 1 minus x, where x takes the values 0 and 1, is called as Bernoulli variate, and its distribution is called as Bernoulli distribution. And as I told, this is the tabular form and this is the functional form of that distribution. And we should always get these values when we take x equal to 1 and 0, we should get p and 1 minus p. Therefore, when you take x equal to 0 in this function, what we get? If you take x equal to 0, it is p raised to 0 is 1. And if you take x equals to 0, it becomes 1 minus p, we say it as. Again, when you take x equals to 1 here, that is p raised to 1 is p. And if you take x equals to 1 here, 1 minus 1 is 0. Anything raised to 0 is 1. 1 into p is p. That means when we take x equals to 1, we get p. When we take x equal to 0, we get 1 minus p in this function. That's why this represents the functional form. That's why we can call it as probability mass function. That's why we define the Bernoulli distribution in the functional form like this. A discrete random variable which has the following property mass function, that is p of x equal to p raised to x into 1 minus p raised to 1 minus x, where x takes the values 0 and 1, is called as Bernoulli variable, and its distribution is called as Bernoulli distribution. And here, in order to write this function completely, we must know one of the constant value, that is p, that is nothing but property of success, and this constant value p is called parameter of the distribution. That means every probability distribution has one function, and that is called as probability mass function, and it has some constant values in order to write that function completely, and those constants are referred as parameter of the distribution. This is a basic distribution that is called as a Bernoulli distribution. It is very much essential to learn the concepts of binomial distribution. And one more thing we have to realize, that when we add the Bernoulli variables, it will give the number of successes. That is one thing. Here we are not mentioned that. That one more note we can say, that is sum of the Bernoulli variable represents number of successes. That you can add into your notes. Now let us discuss the second important distribution, that is called binomial distribution. As we already said, every distribution has one function, probability function, which is known as a probability mass function, and the constants in that function, they are referred as the parameters of the distribution. Now, first let us define what is that binomial distribution. That is, it will be in this fashion: a discrete random variable which has the following property mass function, that is written as PMF, that is given by P of x equals to ncx, p raised to x into q raised to n minus x, where x takes the values 0, 1, 2, 3, so on up to n, and q is the notation stands for 1 minus p, and p is the probability of success. It always lies between 0 and 1. Any discrete random variable which has this as its property mass function is called as binomial variate, and its distribution is called as binomial distribution. Once we notice this distribution carefully, it has two constant values, namely n and p. And we cannot say that q is one more constant, because q is the notation stands for 1 minus p. If we replace that q by 1 minus p, we observe only two constants, namely n and p, and they are called as parameters of the distribution. And a binomial variate with these parameters n and p is denoted as bxnp, or we can say it as x. This symbol stands for follows, that is x follows binomial distribution with parameters n and p. And see, please note down the symbol. This represents follows. That's why I have written here, this symbol is read as follows, means we have to read it as x follows binomial with parameters n and p. Now what this bx and p represents? Means a binomial distribution with parameters n and p represents or gives the probability of getting exactly x successes in n independent Bernoulli trials. Bernoulli trials means the trials which has only two outcomes, where p represents the probability of success. That's why this is an important note. We must know that what binomial distribution gives. Suppose the parameters of binomial distribution n and p are known, then bx and p gives probability of getting exactly x successes in n independent Bernoulli trials, where p represents the probability of success. That will be the note, or that will be the thing we have to realize what this binomial distribution gives. Then the question is, when we can apply distribution, or what are the situation under which we can think of binomial distribution. And the following are the three situations where we can apply the binomial distribution. That's why we have written here, binomial distribution can be applied or can be used under the following situations. The first situation is the number of trials n. Here n is the Bernoulli trial. The number of trials must be finite and independent. Independent means the result of one trial should not affect the result of the another trial. That's the first condition. Second condition is each trial must result in only two outcomes, namely success and failure. Each outcome results in only two outcomes, means one outcome must be success, another outcome must be failure, means each of these n trials are Bernoulli trials, we say. And the third one is the probability of success must remain same in each trial. That is, P is going to be fixed for each trial. Whenever we come across with satisfying these three situations, in that case we can apply binomial distribution. That's why the first condition is the n, the number of trials must be finite and independent. The second one is each trial must result in only two outcomes, namely success and failure. And the third one is probability of success must remain same in each case. It varies from one particular trial to another particular trial, then we cannot apply binomial distribution in this particular situation. Therefore, now let us quote some of the examples of binomial distribution. Now let us list out some of the examples of binomial distribution. And the examples are confirmed as binomial only when they fulfill these three situations. Let us consider the first one. Number of heads obtained when 4 coins are tossed. Here the number of coins tossed is 4, that is n is finite. That's very evident. The second one is the result of one toss will not affect the result of another toss. That means the trials are independent. The first condition is okay. Once you go with the second one, if you take each trial or any trial, it will result in only two outcomes, namely one is success, another is failure. That's why it fulfill the second condition also. And once, if you take the experiment of tossing of a coin, if we toss that coin any number of times, the probability of a success, that is probability of getting hit, remains same in each toss. That's why this particular example fulfills all the three situations of binomial. That's why we can say that it is an example of binomial. Now let us go to one more, that is number of girls in a family of 5 children. And the family consists of 5 children. That's a finite one. And if you take any newborn baby, it may be either a boy or a girl. Means every trial results in only two outcomes, and the probability of having a boy or a girl for each newborn baby, that is going to be same. That is 50% chance of having a boy or a girl. That's why again it fulfills all the three situations. Similarly, once you go to the third one, that is number of bombs hitting the target when 10 bombs are dropped. Okay, and here how many bombs are dropped? 10. That is finite. And once you take any bomb, it has only two options. It may hit the target or it may miss the target. If it hits, that is called success. If it misses, that is called failure. Again, every trial has only two outcomes, namely success and failure. When all the bombs are dropped from the same height, the probability of hitting the target remains same for all the 10 bombs. That's why the third condition also fulfilled. And similarly, we can quote one more, that is number of defective articles in a lot of 100. That is 100, that's a finite one. If you take any article, it has only two options, that it may be defective or it may be non-defective. If it is defective, it is called failure. If it is non-defective, we call it as a success. When all the articles are produced by the same company, the probability of having defective or non-defective item remains same for all the articles. That's why in this case also we can observe all the above situation. That's why it is also an example of binomial variable. Now let us know what are the mean and variance of binomial distribution. Suppose x is a binomial variate with parameter n and p, then its mean is given by n into p and the variance is given by npq, and the standard deviation is given by square root of this, that is square root of npq. Just if you remember these results, that is enough to solve the example. But they have the derivation, but the derivation is beyond the scope of the syllabus. And one more thing we must remember, how to get the theoretical or expected frequencies. And the theoretical or expected frequency of binomial distributions are obtained using the result f of x equals to n into p of x, that is capital N, where capital N represents the total frequency, that is summation f, we can say it as. P of x represents the probability of getting exactly x successes, and f of x represents the frequency of getting exactly x successes. P of x represents probability of getting exactly x successes, and f of x represents the frequency of getting exactly x successes. And here we must note that here whenever the theoretical frequencies are asked, we have to use the result f of x equals to n into p of x. That we have to keep in mind while solving the examples. Now let us go with some examples on binomial distribution. Let us go with the first one. The mean and variance of a binomial distribution are 4 and 4 by 3 respectively. Find probability of the variable x takes the values greater than or equals to 1. And one thing must be kept in mind while solving the examples on probability distribution, that in order to write the probability mass function or probability density function, knowing of the parameter is must. Using the given information, first of all, we must find the parameters of the distribution. In this case, we are discussing binomial distribution. That's why we know that the two constants, namely n and p, are the parameters. Therefore, first, using the given information, we have to find the two parameters, namely n and p. So first, I'll consider, or we'll say that let x follows binomial distribution with parameters n and p. And they are given the first, our intention is to find n and p using the given information. And in this case, they are given that mean of the distribution is 4 and variance of the distribution is 4 by 3. That means here mean of the distribution is np. In this case, they are given it as 4. Let us take it as equation 1. And variance of the distribution is npq, that we have listed here. That is, in this case, they are given it as 4 by 3. Let us take it as equation 2. Once we divide equation 2 by equation 1, the LHS is npq divided by np, and that one equal to 4 by 3 divided by 4. 4 will get cancels. On LHS, np will get cancels. We find q equals to 1 by 3. And q is 1 by 3, and we know that q is a notation which represents 1 minus p. Therefore, 1 minus p equals to 1 by 3. That indicates p equals to 1 minus 1 by 3, that is 2 by 3. Now we got one of the parameter, that is p. Now using this value of p in equation 1, we can get the value of n. That's why n into p value is 2 by 3 equals to RHS is 4. Once you solve this one for n, we get n equals to 6. Now we got the two parameters, namely n and p. Therefore, we can say that x follows binomial with n equal to 6 and p equals to 2 by 3. And we can write the product mass function or product function of binomial, that is given by ncx p raised to x into q raised to n minus x, where x takes the values 0, 1, 2, 3, so on up to n. And n is 6, that is 6cx, p is 2 by 3, that is 2 by 3 raised to x, and q is 1 by 3 raised to n minus x, means 6 minus x, where x takes the value 0, 1, 2, 3 up to n, but in this case n is 6, that's why here x takes the values 0, 1, 2, 3 up to 6. Now, after our actual requirement is we have to find property of x is greater than or equal to 1. Now let us consider that property of x is greater than or equal to 1. Suppose if we go directly, means if I think the permissible values which are greater than or equals to 1. Greater than or equal to 1 means 1, 2, 3, 4, 5, 6. 6 probabilities we have to consider, and we have to add all those 6 properties in order to get that. Otherwise, we can think of complement law, that is probability of any event equals to 1 minus part of its complement. Accordingly, here the event is x is greater than or equal to 1, and we know that the complement of greater than or equal to is less than 1. That's why we can write probability of x is greater than or equal to 1 as 1 minus probability of x is less than 1 according to this law. Then 1 minus probability of less than 1. Less than 1, we have only one option for x, that is 0. That we write p of x equals to 0, and this can be written as p of 0. P of x equal to 0 means p of 0. That is one more notation for that. 1 minus, and we know we want p of 0 now, but we know p of x. Wherever x is there, you take 0 now, that gives you 6c0, 2 by 3 raised to 0, 1 by 3 raised to 6 minus 0. 6 0 is 1, 2 by 3 raised to 0 is 1. Simply we will find 1 by 3 raised to 6. Once you calculate this one using calculator, we find it as 0.9999. That is the probability that the variable x takes the value greater than or equal to 1. Means with this example, we realize that in order to calculate the probabilities for any distribution, first of all, we have to write its probability function completely. In order to write the probability function completely, we must know the values of the parameters of the distribution. Suppose if it is given directly, we can use that. Otherwise, if they give some information to compute that, using those informations, you have to compute the parameters of the distribution. Then we have to write the probability function. Then we have to go for the required calculation. Now let us go for one more example. That is, its go like this. 6 coins are tossed. Find the probability of getting first one exactly 3 heads, second one at least 3 heads, third one at most 1 head. And first we should realize what is success here, because binomial distribution gives probability of getting exactly x successes. If you see here, in each of the requirement we need the probability of number of heads. Here we need 3 heads, here we need at least 3 heads, here we need at least 1 head. Means here getting head is a success. That's why let us define the variable x as number of heads obtained, and we define n as number of coins tossed. In this case, they are given 6 coins are tossed, that is n equals to 6. And p, it goes in general, we have said p as probability of success. In this case, success is probability of getting head. Therefore, let us say p is probability of getting head. Whenever a normal coin is tossed, probability of getting head and tail are equal, and both are equal to 50%. 50% is 1 by 2. That's why in this case p value is 1 by 2. And once we know p, we can write q as 1 minus p. It is a notation, q is a notation for 1 minus p. That gives 1 minus 1 by 2 equals to 1 by 2. Now we find that x follows binomial with n equal to 6 and p equals to 1 by 2. Now, whether this x is a binomial or not, how we have written this one as binomial? Let us consider this x as number of heads obtained. In this case, n is 6, that is finite. And once you take any coin, okay, or any toss, we find that it will result in only two outcomes, head and tail. Second condition is okay. And the third condition, probability of getting head in each of the 6 tosses will be same, that is equals to 1 by 2. That's why it will fulfills all the 3 situations of binomial. That's why we can write that x follows binomial with n equal to 6 and p equals to 1 by 2. Then let us write the probability function of binomial, that is p of x equals to ncx p raised to x into q raised to n minus x, that is 6cx. N is 6, that is 6cx. P is 1 by 2 raised to x, and q is again 1 by 2 raised to 6 minus x. That 6cx we are written as it is. Once we look at here, base is same, add the powers, x will get cancels, that results as 1 by 2 raised to 6, where x takes the value 0, 1, 2, 3 up to 6. And this is the thing first we need, that is the probability mass function is written completely by knowing the parameters n and p. Then let us go for finding the required first one. We need probability of getting exactly 3 heads. That is probability of getting exactly 3 heads equals to p of x equals to 3, because getting 3 heads means x represents number of heads. That's why we say that probability of getting x equals to 3, that is p of 3. You go here and take x equals to 3 now. That becomes 6c3, 1 by 2 raised to 6. 1 upon 2 raised to 6 is 64, and 6c3 value is 20. That can be written as 5 by 16. That is nothing but your 0.3125 is the probability of getting exactly 3 heads. Now the second requirement is probability of getting at least 3 heads. At least 3 heads means 3 or more heads. That's why here x represents number of heads obtained. That number of heads obtained must be at least 3, means it should take the values greater than or equal to 3. Greater than or equal to 3 means here x takes the values 0, 1, 2, 3, 4 up to 6. Greater than or equal to 3 means 3, 4, 5, 6. Here if you go directly, we have to consider 4 probabilities and we have to add all those 40s. Once if you think the complement of this, that is the complement of greater than or equal is less than, that is we can write this one as 1 minus part of x is less than 3. Less than 3 means that is only we have to deal with only 3 properties, that is 0, 1, 2. That's why less than 3 means the permissible values of x are x equals to 0, 1, 2, and that one equals to 1 minus p of 0 plus p of 1 plus p of 2. Once you go and take x equals to 0, 1, 2 here, we can write that is p of 0 as 1 by 2 raised to 6 into 6 is 0, p of 1 as 1 by 2 raised to 6 into 6c1 plus 1 by 2 raised to 6 into 6c2. And if you take 1 upon 2 raised to 6 as our common term, we can write that one. And when we take 1 upon 2 raised to 6 as our common term, we find here 6c0, 6c1, 6c2. That is 6c0 plus 6c1 plus 6c2. That is 64, and 6c0 is 1, 6c1 is 6, 6c2 is 15. That gives you, it is 22 divided by 64. And if you take the LCM as 64 minus 22, that becomes 42 by 44, or we can write it as 21 by 32. Its value is going to be 0.6563. Now let us go to the last one, that is probability of getting at least one head. At least one head means x represents number of heads. At least one means that variable x should take the value 1 or more. At least one meaning is 1 or more. That is x should realize the values 1 or more. That's why we can write this one as equivalent to probability of x is greater than or equals to 1. And again greater than or equal to 1 means if you go directly, the permissible values for x are 1, 2, 3, 4, 5, 6. You have to go for 6 probability calculations. Rather than that, if you think the complement law, this can be written as 1 minus probability of x is less than 1. Less than 1 means only permissible value is 0. With one property we can manage the situation. That is 1 minus p of x equal to 0, that is 1 minus p of 0, that is 1 minus 6c0 into 1 by 2 raised to 6. Here we have to take x equals to 0 in order to get p of 0. And once you simplify, 6c0 is 1, that is 1 upon 2 raised to 6. 2 raised to 6 is 64. If you take the LCM and say 64 minus 1 is 63, or you can directly calculate with the calculator, it results in 0.9844. Now let us go to the third example. The problem goes like this. The probability that the bomb dropped from an aeroplane will strike the target is 1 by 5. If 6 bombs were dropped, find the probability that first one exactly 2 will strike the target, and second one at least 1 will strike the target. Third one, if 2 bomb hit is enough to destroy the bridge, what is the probability that the bridge is destroyed? And we have to go with this. First of all, realize what is success here, because we are dealing with binomial cues probability of getting exactly x successes. First of all, we have to decide what is success here. Suppose if the bomb dropped strike the target, then that will be treated as success. And that's why we define out of 6 bombs, how many are going to strike the target. That's why we have set the variable x as number of bombs striking the target. And they are given probability of success. That is probability of striking the target, it has 1 by 5. And with this p, we can write q as 1 minus p. That is 1 minus 1 by 5. That one equals to 4 by 5. Now n is number of bombs dropped, that is 6. And in this case, again we observe all the 3 conditions of binomial, that is n is finite, every bomb is going to strike the target or miss the target, and probability of striking the target for each bomb is fixed. That's why we observe all the 3 situations of binomial. That's why we can conclude that the variable x follows binomial with n equal to 6 and p equals to 1 by 5. Once we know the parameters, we can write the party function of binomial, which is given by ncx into p raised to x into q raised to n minus x, where q is 1 minus p. N is 6, that is 6cx. P is 1 by 5 raised to x, and q is 4 by 5, and n is 6, that is 6 minus x. X takes the value 0, 1, 2, 3, 4 up to 6. Now let us go for the first one. Consider probability of exactly 2 bombs will strike the target. Number of bombs striking the target will be 2. That's why I can say that P of x equal to 2, because we have defined x as number of bombs striking the target. In this case, we want 2 bombs to strike the target. That's why we have taken probability of x equals to 2, that is P of 2. And in the probability function, what we have written above, wherever x is there, we have to replace that x by 2. That gives you 6c2, 1 by 5 raised to 2, that is 4 by 5 raised to 6 minus 2. That is 6, 2 is 15. 1 by 5 means 0.2 raised to 2. 4 by 5 means 0.8. 6 minus 2 is 4. Once you take the calculation, we are going to get that value as 0.2458. That's the first one. Second one is probability of at least 1 will strike the target. At least 1 means 1 or more. That's why we can write this one as x. The number of bombs striking the target is greater than or equal to 1. Directly we have to go with 6 parties. Once you think of complement law, we can write this one as 1 minus probability of x is less than 1. That is 1 minus x is less than 1 means that is x equal to 0 is the only permissible value. That's why you take x equal to 0 here. We look at this. If you calculate this, this is 1, this is 1, that is 0.8 raised to 6. The calculation of this one leads as 0.7379. And look at the third. It is here directly they are not given the probability of how many success we want, but they are given some information. The information is if 2 bomb hit is enough to destroy the bridge, what is the probability that the bridge is destroyed? In this case, we want probability that the bridge is destroyed. According to the given information, 2 bomb hit is enough to destroy the bridge. Means minimum 2 bombs should hit the bridge, then only the bridge is going to destroy. If more than 2 hits, then also the bridge is going to destroy. Means in order to destroy the bridge, at least 2 bombs should strike the target or hit the bridge. That's why at least 2 means 2 or more. That is probability of number of hittings must be 2 or more. Then only the bridge is going to destroy. Again, greater than or equal to 2 means many properties you have to deal with. Think of complement. This can be written as 1 minus p of x is less than 2. That is 1 minus p of x is less than 2 means x equal to 0 and 1. They are the permissible values which are less than 2. Again, as we know, the values taken by the random variable are mutually exclusive in nature. That comma stands for or. Or becomes plus. That is 1 minus p of 0 plus p of 1. Let us take the values x equal to 0 and x equal to 1 in p of x. If you go like this, it will be 6c0, say 0.2 raised to 0, 0.8 raised to 6 plus 6c1, 0.2 raised to 1 into 0.2 raised to 5. And the calculation of first one will be 0.2621 and the calculation of the second one will be 0.3932. Once you add up this, it will be like this. 1 minus this will result as 0.3447. Now let us go to the fourth example, and the problem is going to be like this. They have given the probability that the man aged 60 will live up to age 70 is 0.65. Out of 10 men now aged 60, find the probability that at least 7 will live up to 70. Exactly 9 will live up to 70 years and at most 9 will live up to 70 years. And this is the problem. Now first we have to realize what is success here. Here the success is the man aged should live up to 70. If a man aged 60 live up to the age 70, then that situation will be treated as success. That's why now here we are going to define x as number of success. Here success is a man living at the age 60 will live up to the age 70. That's why we say that the number of persons now aged 60 will live up to 70 years. That will be the variable, that is number of persons. And in this case, success is living from age 60 to 70 is the success. Now we can write P, what we said as part of success, that part of living from age 60 to 70, and that is given by 0.65. And Q is 1 minus P, that will be 1 minus 0.65 is 0.35. And N is number of men we have considered, that is in this case 10. Again, with respect to variable X, we observe all the three situations, that is N is 10 and probability of survivable remains same for all the 10 men, and for every man the two possibilities are he may live up to 70 or he may not live up to 70. If he lives up to 70, we call it as a success. If we may not live up to 70, we call it as a failure. For every man there are two options. That's why we observe all the three situations of binomial, so we can confirm x is binomial with n equal to 10, that is parameters, and p equals to 0.65. Using these parameters, we can write the probability function of binomial, that is ncx, p raised to x, q raised to n minus x, and n p values are known. That's why we can write this one as 10cx, 0.65 raised to x, and q is 0.35 raised to 10, n minus x means 10 minus x. This case, x takes the values 0, 1 to up to 10. Now let us concentrate on the first requirement, that is a man aged 60 will live up to 70. That is our success. In this case, we want at least 7 people live up to 70. That's why we want property that at least 7 people or persons will live up to 70. Means that X you are defined as number of persons aged 60 will live up to 70 years. That's why this variable should take the value At least 7 means 7 or more. 7 or more means once you take here, it may be 7 or 8 or 9 or 10. Again, that comma stands for or becomes plus. Once you take x equal to 7, 8, 9, 10 in this positive function, we have to write like this. Once you calculate individual values, they may result like this. Once you add these values, it will result like this. That means 0.5139 represents the probability that out of 10 persons, at least 7 will live up to 70 years. Now, in the second case, we want probability that exactly 9 will live up to 70 years. Means, in this case, that x should realize the value 9, that is as good as p of 9. In the probability function, what we have written here, if we take x equals to 9, it will be p of z, that is here, that will be, if you take x equal to 9, that becomes 10c9, 0.65 raised to 9, 0.35 raised to 10 minus 9, that is 1 will get. Once calculate, it will result like this. That means out of 10 people, 9 will live up to 70 years. Probability of that is given by 0.0725. The third one, at most 9 will live up to 7 years. At most means maximum 9 members, or it may be less than that. In this case, x is going to realize values less than or equal to 9. The meaning of at most 9 means the variable x can take less than or equal to 9. At most means maximum is 9, otherwise less than that. That's why it will be x is less than or equal to 9. Less than or equal to 9 means 0, 1, 2, 3, up to 9. Many properties we have to deal with. Instead of that, let us use the complement law. This can be written as 1 minus probability of x is greater than 9. According to this rule, probability of any event equal to 1 minus probability of its complement. Greater than or equal to 9 means here we can realize that only one value is permissible, that is x equals to 10. That is 1 minus p of 10. If you take x equals to 10 here, we'll get this one, and the calculation of this will result as 0.9865. This is the probability that out of 10 men, at most 9 will live up to 70 years. Now let us go to the fifth example. It is going to be like this. If 10% of the pens manufactured by a company are defective, find the probability that out of 12 randomly selected pens, first one exactly 2 will be defective, second one at least 2 will be defective, third one at least 1 will be defective, fourth one none will be defective. And here first of all let us realize what is success here. That is, being a defective, that will be going to be success in this case. That's why we say that x has number of defective pens out of 12. It is understood. And p is the probability of success, means here the success is being a defective. That's why we say that p has probability that a pen is defective. They are given 10% of the pens manufactured by a company are defective, means 10% means 10 by 100, that one equals to percent means with respect to 100, that is 10 by 100 equal to 0.1, and q equal to 1 minus p, that is 1 minus 0.1 is 0.9, and n is number of pens chosen at random, that is in this case they are going to as 12. In this case also, for this variable x, we observe all the three conditions of binomial. This is finite, and being defective is same for all, and for every pen only two options, being defective or being non-defective. That's why we can conclude x is a binomial with n equal to 12 and p equals to 0.1. Once use these parameters, n equal to 12 and p equal to 1.1, the probability function of binomial or probability mass function of binomial, that is ncx p raised to x q raised to n minus x equals to 12cx 0.1 raised to x, and q is 0.9, that is 0.9 raised to 12 minus x, where x takes the value 0, 1 up to 12. Now let us concentrate on the first requirement is exactly 2 pens will be defective, means x, the variable x should realize the value 2. If we take x equals to 2, we'll get that one like this. Second one, at least 2 will be defective. At least 2 means the variable x should take the value 2 or more. That's why we have written part of x is greater than or equal to 2. Again, greater than or equal to 2 means 2 to 12, near about 10 properties you have to consider. That will be a tedious task. That's why we can think of the complement law. This can be written as 1 minus p of x is less than 2 because the complement of greater than or equal is less than. So it is 1 minus p of x equals to 0 and 1 because less than 2, the only two permissible values are 0 and 1. Again, this 0 and 1 can be written as 1 minus p of 0 plus p of 1 as the values are mutually exclusive. And p of 0, take x equal to 0, you'll get this. Take x equal to 1, you'll get this. The value of this one is going to be this using the calculator, and the value of this one, once we calculate using the calculator, will be result like this. The sum of these two will be this, and 1 minus this, that will be 0.341. At 0.341 represents probability of having at least 2 defectives in out of 12. Third one is at least 1. That's again it will greater than or equal to 1. Using the complement, it will be 1 minus x is less than 1. Less than 1 means permissible value is 0. That becomes 1 minus p of 0. Once you take x equals to 0 here, that will be 1 minus point. This becomes 1. This becomes 1. When you take x equal to 0, this becomes 1. Simply look at 0.9 raised to 12. That will be 0.7176. None will be defective means no defective means the variable should take the value x equal to 0. Once you take x equal to 0 here, okay, it will give 1 minus, sorry, 0.9 raised to 12. That will be this. Now, this one is somewhat different, and it is like this. A die is thrown 8 times. Find the probability that the number 3 falls. First one exactly 2 times. Second one at least once. Third one at most 7 times. Here, success is getting a phase 3 whenever a die is rolled. That's our success. And we are going to define x as number of times the phase 3 comes out. Phase 3 false. That will be the variable what we will define. And 3 is a property of getting a phase 3 when a die is rolled. When a die is rolled, we'll get 6 outcomes. That's equally likely cases are 6. Out of x, phase 3 is going to be only 1. That's why 1 by 6 is the probability of getting phase 3 whenever a die is rolled. And q is 1 minus p. That is 1 minus 1 by 6 is 5 by 6, and n is number of times a die is rolled. In this case, again it is rolled n times. Again, for this variable x, we observe all the 3 situations of binomial that n equal to 8 is finite. For every toss, probability of getting that phase 3 is fixed, that is 1 by 6. And these, for every toss, it may getting phase 3 and non getting phase 3. There are only 2 options. That's why we confirm all the 3 situations of binomial. That's why we can conclude that here x follows binomial with n equal to 8 and p equal to 1 by 6. Using these parameters, the binomial property function can be written in this fashion. And now let us go for the requirement. The first requirement, the phase 3, that is number 3 occurs exactly twice, means in this case x should take the value 2. If you take x equal to 2, you'll get this. Second one, the phase 3 occurs at least once, means that x must be greater than or equal to 1. Using the complement law, we can write like this. That is less than 1, only permissible value is 0. That's why it is 1 minus p of 0. And once you take x equal to 0 here, it will be 5 by 6 raised to 8. Its calculation results in the value 0.7674. And the third one, we want that number 3 occurs at most 7 times. At most 7 times means maximum 7 times, otherwise it should be less than that. That's why plot of x is less than or equal to 7. And less than or equal to 7 means again we have to deal with many of the properties. it goes tedious directly. Let us think of complement law, that this can be written as 1 minus part of x is greater than 7. Greater than 7 means only one permissible value. As we observe, in this case, x takes the values from 0, 1 to up to 8. That's why we can write part of x equals to 8. That is 1 minus p of 8. And when you take x equals to 8 here, it will result as 1 minus 1 by 6 raised to 8, and its calculation leads to 0.9999. And one last problem in this case, in this problem, instead of getting the probabilities, we are asked to find the theoretical frequencies. But in order to get the theoretical frequencies, getting the corresponding probabilities is must. Now first let us look at the problem. What is the statement of the problem? Out of 800 families with 5 children each, how many families do you expect to have 3 boys, 5 girls, either 2 or 3 boys? Once you look at this problem, we are not going to observe any word like probability, but they asked how many families. That indicates in this problem, instead of probability, they asked frequency. But as we already stated, the theoretical frequencies are obtained using the rule, that is f of x equals to n into p of x. Because of that, in order to find the frequency, finding the corresponding probability is must. That's why first let us define the usual things. In this case, once you look at the requirement, here we want 3 boys, here we want 5 girls. Out of 5 children, if all the 5 are girls, in that case that indicates no boys. Saying 5 girls is as good as no boy. That is 3 boys, 0 boys, either 2 or 3 boys. That indicates the interest is with respect to number of boys. That's why let us say we can conclude that having a boy is a success here. That's why let us take x as number of boys in the family, and p is probability of having a boy. In this case, for any newborn baby, probability of having a boy and girl are equal, and both are equal to 1 by 2. That's why we can conclude p equals to 1 by 2. So q is 1 minus p, again it will be 1 by 2. And n is number of children in a family. They are given a family consists of 5 children, and capital N is number of families, and in this case that is nothing but your 800. Now again this variable x, we already explained many of the times, it is a good example of binomial. That's why we can conclude x is binomial with n equal to 5 and p equals to 1 by 2. With these values of n and p, we can write the probability function of binomial as, that is ncx p raised to x into q raised to n minus x as 5cx into 1 by 2 raised to x into, again q is 1 by 2 raised to 5 minus x. Base is same, add the powers, x will get cancels, 1 by 2 raised to 5 to 5cx, where x takes the values 0, 1, 2, 3 up to 5. Now let us concentrate on the first one. In the first case, we want how many families with 3 boys. That's why number of families having 3 boys, exactly 3 boys equals to capital N into f of x. That is n into f of x, sorry, p of x. That is as I told, f of x equals, as theoretical frequencies are obtained as f of x equal to n into p of x, where n is the total frequency and p of x is the probability of getting exactly x successes. In this case, we want 3 successes. That's why we have written p of x equals to 3. This will be 800, and p of 3 I can write. In this problem, if it function, if you take x equal to 3, it will be 800 into 1 by 2 raised to 5 is that 2 raised to 5 and 5c3, and this is 800. 1 upon 2 raised to 5 is 32 and 5c3 is 10. If you calculate this, that results in 250. That means out of 800 families, there are 250 families having exactly 3 boys in their family. That will be the approximate calculation. And the second calculation says number of families having 5 girls. Having 5 girls means number of families having no boys. No boys. Again, we want a frequency that will be given by n into p of x. In this case, p of x is product of having no boy. That means product of x equals to 0. N is 800 and x equal to 0 can be written as p of 0. Once we take x equals to 0 here, that gives 1 upon 2 raised to 5 to 5c 0, and 1 upon 2 raised to 5 is 32, 5c 0 is 1. That becomes calculation is 25. Means out of 800 families, there are 25 families having 5 girls, or we say no boys in their family. The last one, number of families having either 2 or 3 boys. That means capital N into corresponding priority means priority of having 2 or 3 boys. That is capital N is 800, P of x equal to 2 or 3. Again this or becomes plus. That is P of x equal to 2 plus P of x equal to 3. P of x equal to 2 can be written as P of 2 and this one is P of 3. And we can take x equal to 2 and x equal to 3 in this product function. We can write it as 1 by 2 raised to 5 to 5c2 plus 1 upon 2 raised to 5 to 5c3. And I can take 1 upon 2 raised to 5 as common here. This is 5c2 is 10, 5c3 is 10. That means 2 raised to 5 is 32, 10 plus 10 is 20. This will be 250 into 20. That results in 500. That indicates out of 800 families with 5 children, out of 800 families with 5 children, there are 500 families having either 2 or 3 boys. That will be the required frequency, that is number of families having 2 or 3 boys. And this is all about the discussion on binomial distribution and the discussion on examples on binomial distribution. In our next video, let us concentrate on the third distribution, that is Poisson distribution, that we can discuss in next class. Thank you.